Imagine you're standing at a cosmic finish line, watching the universe's ultimate race. Everything that exists, light, matter, energy, information, is competing to see what can cross the cosmos fastest. And the winner, every single time for the past 13.8 billion years, is light. Today, we're going to discover why the speed of light isn't just fast. It's the absolute boundary woven into the very fabric of reality itself. If you are curious about these cosmic mysteries, make sure to subscribe to the channel and hit that like button. And here is a question for you. If you could travel at the speed of light right now, where's the first place you'd go? Let me know in the comments down below. I will pin the most creative answer. Let's start with a simple question that leads us down a rabbit hole of cosmic insights. Why does anything have a maximum speed at all? In our everyday experience, if you want to go faster, you just apply more force. Push harder on the gas pedal, and your car accelerates. So why can't we just keep adding energy to something until it goes faster than light? The answer isn't what you might expect. The universe doesn't work like a highway with a posted speed limit that you could break if you had a fast enough vehicle. Instead, the speed of light limit emerges from the fundamental structure of spacetime itself. To understand this, we need to think about what happened in 1905, when a young patent clerk named Albert Einstein published a paper that would revolutionize everything we thought we knew about motion, space, and time. Einstein started with a deceptively simple observation. The speed of light appears to be the same for everyone, no matter how fast they're moving. Think about how strange this is. If you're on a train moving at 100 kilometers per hour and you throw a ball forward at 20 kilometers per hour, someone standing on the platform sees the ball moving at 120 kilometers per hour. That's basic addition, right? But light doesn't follow this rule. Whether you're standing still or racing through space at half the speed of light, when you measure a beam of light, it always moves at exactly the same speed. Always. This bizarre fact isn't just a quirk of light. It's a clue that space and time themselves work differently than we intuitively expect. Einstein realized that for the speed of light to be constant for all observers, space and time must be flexible, relative, interconnected. His special theory of relativity showed that space and time aren't separate, fixed stages on which events unfold. Instead, they're woven together into a single fabric called spacetime. And here's the crucial insight. The speed of light isn't really about light at all. It's the speed at which causality propagates through the universe. It's the maximum rate at which cause and effect can operate. It's the conversion factor between space and time in the equations that describe our universe. Think of spacetime as having a built-in speed limit the same way that sound has a maximum speed in air. Sound travels by compressing air molecules, which then push on neighboring molecules. The speed of sound depends on how quickly those molecules can transmit the pressure wave, which depends on the properties of air. You can't make sound travel faster than air molecules can respond to pressure changes. It's not a limit on the sound itself, but a limit imposed by the medium carrying it. Similarly, the speed of light is the maximum rate at which information can propagate through spacetime. This limit isn't arbitrary. It emerges from the geometry of spacetime itself. And here's where things get truly mind-bending. When objects approach this speed limit, spacetime itself warps around them in ways that prevent them from ever crossing that boundary. Let me explain what happens as you try to accelerate something closer and closer to light speed. As an object moves faster, three extraordinary things occur, all interconnected and all conspiring to prevent anything from exceeding the cosmic speed limit. First, time slows down for the moving object relative to a stationary observer. Second, the object's length contracts in the direction of motion. Third, the object's mass increases, making it harder and harder to accelerate further. These aren't just theoretical predictions. We observe these effects every single day. At the Large Hadron Collider near Geneva, Switzerland, physicists accelerate protons to 99.999991% the speed of light. At these incredible speeds, the protons behave exactly as Einstein's equations predict. Their lifetimes extend due to time dilation. They appear contracted in their direction of motion. And most importantly, they become harder and harder to accelerate as they approach the speed of light. Here's the crucial point. It's not that we lack powerful enough engines or sufficient energy to push these protons to light speed. The universe itself changes the rules as you approach the limit. The faster you go, the more massive you become, and the more energy is required to accelerate you further. As you approach the speed of light, your mass approaches infinity. The energy required to accelerate you further also approaches infinity. Infinity is a mathematical concept, not something that can actually exist in the physical universe. You can't have infinite mass or infinite energy. This means that reaching the speed of light is literally impossible for anything with mass. You can get closer and closer, 99%, 99.9%, 99.999%, but you can never actually reach 100%. The universe has built this barrier into its very foundation. Now, you might be thinking, what about light itself? How does light travel at the speed of light if nothing can reach that speed? This is where things get beautifully elegant. Light doesn't accelerate to light speed. It's always traveling at that speed from the moment it's created. And here's why photons, the particles of light, have zero mass. They don't experience the infinite mass problem. In fact, for massless particles, the only speed they can travel at is the speed of light. They can't go slower, and they can't go faster. This reveals something profound. The speed of light is really the speed of anything massless. It just happens that light is the most familiar example of a massless particle traveling at this cosmic speed limit. Gravitational waves, discovered by the LIGO Observatory in 2015, also travel at exactly this speed because they too are massless disturbances in spacetime. When LIGO detected gravitational waves from two merging neutron stars in 2017, astronomers also observed light from the same event. The waves and the light arrived within seconds of each other after traveling 130 million light-years, confirming that gravity propagates at light speed. But here's a question that might be nagging at you. If the speed of light is truly unbreakable, how do we explain phenomena that seem to exceed it? You might have heard about quantum entanglement, where particles appear to communicate instantaneously across vast distances, or cosmic expansion, where distant galaxies recede from us faster than light, or those jets from black holes that appear to move at several times light speed. Don't these violate the cosmic speed limit? The answer is fascinating and reveals just how clever the universe is at preserving this fundamental boundary. Each of these apparent violations turns out to respect the speed of light limit in subtle but important ways. If you're curious about diving deeper into these cosmic loopholes and apparent exceptions, I actually made a detailed video exploring whether the speed of light is really the fastest speed in the universe. It covers quantum entanglement, warp drives, and all those mind-bending scenarios. The link is in the description and pinned in the comments if you want to check it out after this. Let me give you a taste of what's happening with these apparent exceptions. Take quantum entanglement. When two particles are entangled, measuring one instantly affects the other, even across cosmic distances. This seems to violate the light speed barrier. But here's the subtle point. While the correlation is instantaneous, you can't use it to send information faster than light. The measurement results are random, so you can't encode a message. The universe allows instant quantum correlations while prohibiting faster than light communication. It's like having two magic coins that always land on opposite sides, but you can't control which side yours lands on, so you can't send signals. Or consider cosmic expansion. Space itself can expand faster than light, carrying distant galaxies away from us at superluminal speeds. But nothing is moving through space faster than light. Space itself is growing. It's a crucial distinction. General relativity, Einstein's theory of gravity and spacetime, places limits on motion through space, but not on the expansion of space itself. The cosmic speed limit still holds for everything moving through spacetime. Now let's dig deeper into why this speed limit exists at all. The answer connects to one of the most fundamental principles in physics, causality. Cause must precede effect. If you could send information faster than light, you could create situations where effects happen before their causes, leading to paradoxes that would break the logical consistency of the universe. Here's how this works. In Einstein's relativity, observers moving at different speeds experience time differently. Events that are simultaneous for one observer might not be simultaneous for another. This is fine as long as information travels at light speed or slower. Everyone agrees on the order of cause and effect. But if information could travel faster than light, different observers could disagree about whether the cause or the effect happened first. You could theoretically send a message into your own past, creating grandfather paradoxes and logical impossibilities. The universe seems to avoid this by making the speed of light the absolute limit. It's as if the cosmos has chosen logical consistency over unlimited speed. The price we pay for a universe where cause reliably precedes effect is that nothing can travel faster than light. It's not just a physical limit, it's a logical necessity for a consistent universe. This brings us to one of the most beautiful aspects of the speed of light limit. It creates what physicists call light cones. Imagine you're sitting at a particular point in space and time. The future light cone consists of all events that you could possibly influence, everything you could reach by traveling at or below light speed. The past light cone consists of all events that could have influenced you. Everything outside your light cone is causally disconnected from you at this moment. You can't affect it, and it can't affect you. These light cones create a structure to spacetime, a web of causal relationships that connects every event in the universe's history. The speed of light limit isn't a barrier that isolates us. It's the thread that weaves the cosmic tapestry together. Every photon that reaches your eye from a distant star has traced a path through space-time, connecting that star's past to your present. You're linked to distant galaxies through chains of cause and effect that respect the cosmic speed limit. The Hubble Space Telescope has captured images of galaxies over 13 billion light-years away. The light in those images has been traveling for 13 billion years, meaning we're seeing those galaxies as they were when the universe was less than 1 billion years old. This is possible because of the finite speed of light. If light traveled infinitely fast, we'd see everything in the universe as it is right now, losing the ability to peer into cosmic history. The speed of light limit gives us a time machine, allowing us to observe the universe's past by looking at distant objects. The James Webb Space Telescope, launched in 2021, pushes this even further. Its infrared vision allows it to see galaxies that formed just a few 100 million years after the Big Bang. These ancient galaxies are so distant that their light has been traveling for over 13 billion years. We're literally looking back in time, witnessing the universe's infancy. And this cosmic archaeology is possible only because light travels at a finite speed, taking time to cross the vast distances of space. Now let's explore what happens at the level of particles and energy. Einstein's most famous equation, E equals mc squared, connects mass and energy. This equation tells us that mass is just condensed energy, and energy has mass. When you add energy to an object to make it go faster, you're not just increasing its speed, you're also increasing its mass. The faster it goes, the more massive it becomes, and the harder it becomes to accelerate further. At everyday speeds, this effect is negligible. When you drive faster in your car, your mass increases by an amount so tiny that the most precise scales in the world couldn't measure it. But at speeds approaching light speed, the effect becomes dramatic. At 90% the speed of light, an object's mass is about twice its rest mass. At 99% light speed, it's about 7 times heavier. At 99.9%, it's over 22 times heavier. This mass increase isn't an illusion or a measurement artifact. It's real, and it has real consequences. Particle accelerators must account for it. At the Large Hadron Collider, the magnetic fields that steer protons around the 27-kilometer ring must be incredibly powerful to bend the paths of particles whose mass has increased by a factor of over 7,000. The protons moving through that circular tunnel are nearly 7,500 times more massive than when they're at rest. Here's another way to think about it. As you add energy to an object moving near light speed, almost all that energy goes into increasing the object's mass rather than its speed. You can keep pumping in energy forever, and the object will get more and more massive, but its speed will asymptotically approach the speed of light without ever reaching it. It's like trying to reach the horizon. No matter how far you walk, it's always the same distance away. The mathematics of special relativity describe this precisely. There's a factor called gamma that appears in the equations, and it equals 1 divided by the square root of 1 minus v squared over c squared, where v is velocity and c is the speed of light. When you're moving slowly compared to light speed, gamma is very close to 1, and relativistic effects are negligible. But as you approach light speed, the denominator approaches 0, and gamma approaches infinity. Time dilation, length contraction, and mass increase all depend on this gamma factor. Scientists at CERN have verified these equations to extraordinary precision. Muons, unstable particles created when cosmic rays hit the atmosphere, normally decay in about 2 microseconds. But when muons are created in particle accelerators at speeds close to light, they live much longer from the laboratory's perspective. Muons moving at 99.9% light speed live about 22 times longer than stationary muons, exactly as Einstein's equations predict. Time literally slows down for them. This time dilation isn't just some abstract mathematical curiosity. It has practical applications. The global positioning system relies on satellites orbiting Earth at high speeds. These satellites experience less gravity than objects on Earth's surface and also move at significant velocities. Both effects influence the rate at which time passes for the satellite's atomic clocks. If engineers didn't account for relativity, both special and general, GPS positions would drift by about 10 kilometers per day. Every time your phone tells you your location accurately, it's confirming Einstein's theories. Let's shift perspective and think about what the speed of light limit means for our cosmic neighborhood. The nearest star to our Sun, Proxima Centauri, lies about 4.2 light-years away. This means light from that star takes 4.2 years to reach us. If we could somehow build a spacecraft that traveled at 99% the speed of light, the journey would take a bit more than 4 years from Earth's perspective. But here's the mind-bending part. Because of time dilation, the astronauts aboard would experience much less time passing, perhaps only about 7 months. This creates the famous twin paradox. Imagine twins, one staying on Earth and one traveling to Proxima Centauri and back at near light speed. When the traveling twin returns, they'd be younger than their Earth-bound sibling. This isn't science fiction. It's a real consequence of relativity, verified by experiments with atomic clocks on airplanes and satellites. Time genuinely passes at different rates depending on your motion through space. The Andromeda Galaxy, our nearest large galactic neighbor, lies about 2.5 million light-years away. Even traveling at 99.999% the speed of light, the journey would take over 2.5 million years from Earth's perspective. However, due to time dilation, the travelers would experience only about 1,800 years, still far too long for any human lifetime, but dramatically shorter than Earth-based observers would measure. The speed of light limit combined with time dilation creates strange asymmetries in how different observers experience cosmic journeys. Now here's something that really drives home why the speed of light matters for the structure of our universe: the cosmic microwave background radiation. This is light from the Big Bang itself, stretched and cooled by cosmic expansion over 13.8 billion years. The Planck satellite mapped this radiation with exquisite precision, revealing tiny temperature fluctuations that represent the seeds of all cosmic structure, the spots where galaxies, stars, and eventually planets and life would form. These temperature variations are incredibly small, less than 1 part in 100,000. They're so uniform because the early universe underwent a period called inflation, where space expanded faster than light for a brief moment, smoothing out irregularities. After inflation ended, different regions of space were causally connected through light-speed interactions, creating the patterns we observe. The finite speed of light shaped the very distribution of matter and energy throughout the cosmos. Consider what would happen if light traveled infinitely fast. The universe would look fundamentally different. Chemical reactions depend on electromagnetic forces, which propagate at light speed. If those forces acted instantaneously, atoms might not be stable. Electrons orbit nuclei because of the balance between electromagnetic attraction and quantum uncertainty. Change the speed of light, and you change chemistry itself. Carbon, the basis of life, might not exist. Stars might not shine. The universe as we know it could not be. The fine structure constant, a dimensionless number that characterizes the strength of electromagnetic interactions, depends on the speed of light. This constant is approximately 1/137, and it determines everything from the spectral lines atoms emit to how tightly electrons are bound to nuclei. If the speed of light were different, this constant would change, and the entire periodic table would be reorganized. The universe would be chemically alien, perhaps incapable of supporting complexity or life. Let me tell you about an experiment that beautifully demonstrates the reality of the light speed limit. In particle accelerators, when electrons moving at 99.9999% light speed collide with nearly stationary protons, the collision creates showers of exotic particles. Some of these particles, like neutral pions, decay almost instantly into photons. Despite the electrons moving at essentially light speed before the collision, the photons produce travel at exactly light speed, not faster, not slower. The photons don't inherit the electron's velocity in a simple additive way. They travel at c, always and only. This connects to another profound insight. Light always travels at the same speed in vacuum, but it experiences neither space nor time. From a photon's perspective, if we could somehow adopt that perspective, the journey from a distant galaxy to your eye happens instantaneously. The photon is created and absorbed in the same moment of its existence. It crosses billions of light years without experiencing time passing. This is what happens when you travel at the cosmic speed limit. Time dilation becomes infinite. You become frozen in time, experiencing eternity in an instant. But we cannot adopt a photon's perspective, and there's a deep reason why. To have a perspective, to be an observer, requires that you have mass and therefore travel slower than light. Consciousness, thought, information processing, all of these require causal interactions which require time to pass. Massless particles traveling at light speed don't experience time and therefore can't be observers. The speed of light limit separates the universe into two categories: massive particles that can observe and interact, traveling slower than light, and massless particles that carry forces and information, traveling at light speed. This dichotomy isn't arbitrary. It emerges from the mathematical structure of special relativity and quantum field theory. Massive particles are described by one set of equations, massless particles by another. You can't smoothly transition from one to the other. There's a fundamental discontinuity at the speed of light. Particles either have mass and travel below light speed, or they're massless and travel at light speed. Nothing exists in between. Now let's talk about something called Cherenkov radiation, which beautifully illustrates the difference between the speed of light in vacuum and the speed of light in materials. When light travels through transparent materials like water or glass, it slows down. In water, light travels at about 75% of its vacuum speed. But particles from nuclear reactions can move faster than this reduced speed, while still being slower than the vacuum speed of light. When a charged particle travels through water faster than light travels through water, it creates the optical equivalent of a sonic boom, a shock wave of light called Cherenkov radiation. This produces the characteristic blue glow you might have seen in photographs of nuclear reactors underwater. The particle isn't breaking the cosmic speed limit. It's just moving faster than light in that particular medium. The cosmic speed limit is specifically about the speed of light in vacuum, which nothing can exceed. The Super Kamiokande detector in Japan uses this principle to detect neutrinos. This enormous detector contains 50,000 tons of ultra-pure water surrounded by 11,000 light sensors. When a neutrino, a nearly massless particle that barely interacts with matter, occasionally collides with a water molecule, it produces charged particles that race through the water faster than light can travel there. These particles emit Cherenkov radiation, creating distinctive rings of blue light that the sensors detect. This technique has revealed neutrinos from the sun, from cosmic ray collisions, and even from a supernova explosion in 1987. Let me address a question you might have. If nothing can exceed light speed, how does the universe expand? During the Big Bang's first moments, space itself expanded so rapidly that regions of the universe moved apart faster than light could travel between them. This continues today. Distant galaxies recede from us faster than light speed due to cosmic expansion. How is this possible if nothing can go faster than light? The answer reveals something subtle about general relativity. Einstein's special theory of relativity says that nothing can move through space faster than light. But general relativity, his theory of gravity, says nothing about how fast space itself can expand. When we say distant galaxies are receding faster than light, we don't mean they're moving through space that fast. We mean the space between us and them is growing so rapidly that the distance increases faster than light could traverse it. It's like dots on a balloon being inflated. The dots aren't moving across the balloon's surface, but the surface itself is stretching, increasing the distance between dots. No individual dot moves faster than light relative to its local patch of rubber, but dots far apart can separate faster than light because of the balloon's expansion. The cosmic speed limit applies locally. Nothing in your local region of space can move past you faster than light. But the cumulative effect of space expansion over cosmic distances can make distant objects recede faster than light. The Hubble Space Telescope and ground-based observatories have measured this expansion by observing distant supernovae. Type Ia supernovae, exploding white dwarf stars, have remarkably consistent brightness, making them excellent cosmic distance markers. By comparing how bright they appear with how bright they should be, astronomers can calculate their distance. By measuring how their light is redshifted, stretched to longer wavelengths by cosmic expansion, astronomers determine how fast they're receding. These observations, conducted in the late 1990s by two independent teams, revealed something shocking. The universe's expansion is accelerating. Not only is space expanding, but it's expanding faster and faster over time. This discovery earned the 2011 Nobel Prize in Physics and revealed that about 68% of the universe consists of mysterious dark energy that drives this acceleration. The current best measurements suggest the universe is expanding at about 70 kilometers per second per megaparsec. This means that for every megaparsec, about 3.26 million light-years of distance between us and a galaxy, that galaxy recedes about 70 kilometers per second faster. Galaxies 100 megaparsecs away recede at 7,000 kilometers per second. Galaxies 1,000 megaparsecs away recede at 70,000 kilometers per second. At sufficient distance, the recession speed exceeds the speed of light. There's a boundary called the cosmic event horizon, currently about 16 billion light-years away. Galaxies beyond this horizon are receding faster than light, which means light they emit now will never reach us. We can still see these galaxies because we're receiving light they emitted in the past, before they crossed the horizon. But they're essentially disappearing from our observable universe. The finite speed of light combined with accelerating expansion means there are regions of space we can never observe or influence, no matter how long we wait or what technology we develop. This creates a profound cosmic loneliness. In the far future, hundreds of billions of years from now, all galaxies outside our local group will have receded beyond the cosmic horizon. Future astronomers will see a universe containing only their merged galaxy, surrounded by darkness. They might never discover cosmic expansion or the Big Bang, because all evidence will have vanished beyond the horizon. The speed of light limit doesn't just constrain our present, it shapes cosmic destiny itself. Now let's talk about gravitational waves, ripples in spacetime itself that travel at exactly light speed. Einstein predicted these waves in 1916 as a consequence of general relativity. When massive objects accelerate, particularly when compact, massive objects like black holes or neutron stars orbit each other, they create disturbances in spacetime that propagate outward like ripples on a pond. These waves literally compress and stretch space itself as they pass. For decades, gravitational waves remained theoretical predictions. Then, on September 14, 2015, the twin LIGO detectors in Louisiana and Washington detected a gravitational wave signal from two black holes merging 1.3 billion light-years away. The signal arrived at the two detectors 7 milliseconds apart, consistent with a wave traveling at light speed across the 3,000 kilometers between detectors. This observation confirmed that gravity itself propagates at the cosmic speed limit. The 2017 detection of gravitational waves from merging neutron stars, accompanied by observations across the electromagnetic spectrum, provided even more compelling evidence. The gravitational waves arrived at LIGO followed about 1.7 seconds later by gamma rays detected by the Fermi Space Telescope. After traveling 130 million light-years, gravity and light arrived within seconds of each other, confirming they travel at the same speed to extraordinary precision. This observation killed dozens of alternative theories of gravity in one stroke. Some theories had proposed that gravitational effects might propagate faster or slower than light. But nature has spoken unambiguously. Gravity obeys the same cosmic speed limit as light. This makes sense because both gravity and electromagnetism are massless force carriers in quantum field theory. Both must travel at the speed appropriate to massless particles. The cosmic speed limit we call the speed of light. Let's dive deeper into why mass creates this barrier. In particle physics, mass comes from interactions with the Higgs field, a quantum field permeating all of space. The Higgs boson, discovered at CERN in 2012, is the quantum of this field. When particles interact strongly with the Higgs field, they acquire large mass. Particles that don't interact with the Higgs field remain massless. Photons, the particles of light, don't interact with the Higgs field. They have no mass and therefore travel at the cosmic speed limit. Electrons interact moderately with the Higgs field, acquiring a small mass, which means they cannot reach light speed. W and Z bosons, which carry the weak nuclear force, interact very strongly with the Higgs field, acquiring large masses, about 80 and 90 times the proton mass respectively. Their large mass makes them very difficult to accelerate and very far from the cosmic speed limit in typical conditions. This connection between mass and speed reveals something beautiful. The Higgs mechanism, which gives particles mass, is also what enforces the cosmic speed limit for those particles. Mass isn't just a measure of how much stuff something contains. It's a measure of how strongly that thing resists changes in motion, how far it is from being able to reach light speed. Massless particles aren't special because they're fast. Massive particles are special because they're slow. Think about the energy scales involved in approaching light speed. At the Large Hadron Collider, each proton receives about 7 trillion electron volts of energy. That's 7 tera-electron volts. A proton's rest mass energy is about 938 million electron volts. So the energy added is nearly 7,500 times the proton's rest mass. Almost all this energy goes into making the proton more massive rather than faster. The speed increases from 0 to 99.999991% light speed, but no amount of additional energy will reach that final 0.009%. Now let me tell you about cosmic rays, high-energy particles from space that constantly bombard Earth. Some of these particles have extraordinary energies. The highest energy cosmic ray ever detected, observed in 1991 and nicknamed the Oh My God particle, had energy around 320 quintillion electron volts. That's 50 joules, about the kinetic energy of a baseball thrown at 90 kilometers per hour, concentrated in a single subatomic particle. Even with this enormous energy, the particle was still traveling just slightly below light speed. The difference was infinitesimal. The particle's speed differed from light speed by only 1 part in 10 to the 23. But it was still slower than light. No matter how much energy a massive particle has, it remains trapped below the cosmic speed limit. The universe simply doesn't allow exceptions. These ultra-high-energy cosmic rays are so close to light speed that they experience enormous time dilation. From the particle's perspective, its journey across the galaxy happens in moments. A cosmic ray created in a supernova remnant thousands of light-years away experiences only microseconds of proper time before striking Earth's atmosphere. It crosses the galaxy in an eye blink of its own subjective time, while thousands of years pass for the galaxy itself. This brings us to a fascinating consequence of the light speed limit, the GZK cutoff, named after physicists Griezin, Zatsepin, and Kuzmin, who predicted it in 1966. These scientists realized that ultra-high-energy cosmic rays should lose energy when they collide with photons in the cosmic microwave background radiation. Above a certain energy threshold, about 5 times 10 to the 19th electron volts, cosmic rays traveling through space should interact with these background photons, creating particles called pions and losing energy in the process. This means that even if cosmic accelerators elsewhere in the universe create particles with energies far beyond the GZK threshold, those particles should lose energy during their journey to Earth. We shouldn't detect cosmic rays above this energy from distant sources. And indeed, observations from the Pierre Auger Observatory in Argentina, which monitors cosmic rays using an array of detectors spread across 3,000 square kilometers, have confirmed the GZK cutoff exists. The most energetic particles reaching Earth come from relatively nearby sources, while more distant sources contribute only lower energy particles. The cosmic microwave background itself provides another beautiful demonstration of the speed of light's role in the universe. This radiation, discovered accidentally in 1964 by Arno Penzias and Robert Wilson, is light from when the universe was only 380,000 years old. Before this time, the universe was too hot for atoms to form. Electrons and protons existed as a plasma that scattered light constantly, making the universe opaque. When the universe cooled enough for electrons and protons to combine into hydrogen atoms, light could suddenly travel freely. The photons released at that moment have been traveling through space ever since, their wavelengths stretched by cosmic expansion from visible light to microwaves. The cosmic microwave background is a snapshot of the universe at that moment, and we can observe it because those photons have been traveling at light speed for over 13 billion years to reach us. The exquisite uniformity of this radiation, it's the same temperature in all directions to within 1 part in 100,000, tells us something profound about the early universe. Regions of space on opposite sides of the sky appear to have the same temperature, suggesting they were once in causal contact, able to exchange energy and equilibrate to the same temperature. But at light speed, there hasn't been enough time since the Big Bang for light to travel between these regions. This is called the horizon problem, and it's one of the major pieces of evidence for cosmic inflation, a period in the universe's first fraction of a second when space expanded faster than light. During inflation, regions that were initially close enough to be in causal contact were stretched apart to distances much larger than light could have traveled in the age of the universe. This explains why the cosmic microwave background is so uniform while respecting the speed of light limit for motion through space. Now let's explore what the speed of light limit means for information and causality. In our everyday world, information seems like an abstract concept, the words in a book, the data on your computer, the message in a conversation. But physics treats information as something physical, something that must be carried by particles or fields, all of which are limited by the speed of light. When you read these words, information is traveling from the screen to your eyes via photons, which move at light speed. The neural signals in your brain processing this information travel much slower, about 100 meters per second, limited by the speed of chemical and electrical signals in neurons. Everything you perceive, every thought you have, every decision you make, is constrained by how fast information can move through physical systems. This has profound implications for consciousness and free will. Your brain is a collection of neurons communicating at chemical and electrical speeds far below light speed. Different parts of your brain can be causally disconnected on timescales of milliseconds. Information from your visual cortex can't instantly reach your motor cortex to influence a decision. Your sense of unified consciousness emerges from countless small causal interactions, all limited by information transmission speeds, which ultimately can't exceed the cosmic speed limit. Quantum mechanics introduces another layer to this story through the no-cloning theorem and quantum information theory. This theorem states that you cannot create an identical copy of an unknown quantum state. Why? Because creating a perfect copy would allow faster-than-light communication through quantum entanglement, violating causality. The universe forbids cloning quantum states precisely to protect the speed of light limit and preserve causality. Researchers at IBM, Google, and other quantum computing companies are developing quantum networks that could transmit quantum information over long distances using entangled particles. These quantum communication systems promise unprecedented security because measuring an entangled particle disturbs its state, revealing eavesdropping. But even quantum communication cannot transmit usable information faster than light. The speed limit remains absolute, protecting causality even in the quantum realm. Let's talk about tachyons, hypothetical particles that always travel faster than light. These particles emerge naturally from certain equations in physics, particularly in string theory, but they have bizarre properties. As a tachyon loses energy, it speeds up rather than slowing down. To slow down to light speed would require infinite energy. And from some reference frames, tachyons would appear to travel backward in time. Despite decades of searching, no experiment has ever detected a tachyon. Every test at particle accelerators, every observation of cosmic rays, every astronomical survey has found exactly zero evidence for faster-than-light particles. Most physicists now believe that when tachyons appear in a theory's equations, they indicate the theory has a fundamental instability rather than predicting real particles. The appearance of tachyons is a red flag suggesting the theory needs fixing. The absence of tachyons isn't just a negative result, it's a positive confirmation that the universe respects causality. If tachyons existed, they would create closed time-like curves, pathways through spacetime that loop back on themselves, allowing time travel into the past. This would permit grandfather paradoxes and logical contradictions. The fact that we observe no such particles suggests the universe is logically consistent, that cause must precede effect, and that the speed of light limit is inviolable. Stephen Hawking proposed what he called the chronology protection conjecture, the idea that the laws of physics somehow prevent time travel and faster-than-light communication. Whenever a scenario seems to allow these phenomena, quantum effects or other physical processes intervene to prevent paradoxes. It's as if the universe has built-in safeguards against causality violations. While we can't mathematically prove this conjecture, every investigation supports it. The universe appears determined to maintain logical consistency. Now let's consider what happens at the quantum level with something called the uncertainty principle. Werner Heisenberg discovered in 1927 that you cannot simultaneously know both the position and momentum of a particle with perfect precision. The more precisely you measure one, the more uncertain the other becomes. This isn't a limitation of measurement technology, it's a fundamental property of nature. The uncertainty principle connects to the speed of light through the concept of quantum fields. In quantum field theory, particles are excitations of underlying fields that permeate all of space. The electromagnetic field, for example, exists everywhere, and photons are its quantum ripples. These fields can't transmit information faster than light because of how quantum mechanics and special relativity combine. Any attempt to measure a quantum field at one location can't instantaneously affect measurements at distant locations separated by space-like intervals. This protection of causality happens through something beautiful called microcausality. In quantum field theory, measurements at space-like separated points must commute. The order doesn't matter, and they don't affect each other. This mathematical requirement emerges automatically when you combine quantum mechanics with special relativity. The universe's quantum nature and its speed limit are deeply intertwined, each reinforcing the other to maintain logical consistency. The Casimir effect provides a fascinating example of quantum field theory in action. When two metal plates are placed very close together in a vacuum, they experience an attractive force. This happens because the quantum fluctuations of the electromagnetic field between the plates are restricted. Only certain wavelengths fit. While outside the plates, all wavelengths contribute. The pressure difference pushes the plates together. This measurable force arises from quantum fields, which themselves respect the speed of light limit in how they propagate. Experiments at institutions like the University of California and various national laboratories have measured the Casimir force with extraordinary precision, confirming quantum field theory's predictions. These measurements verify that even the vacuum isn't truly empty, but seethes with quantum activity. Yet all this quantum activity respects locality and causality. Virtual particles pop into existence and annihilate in times so brief they're called virtual, but they can't carry information faster than light. Let me tell you about neutrinos, nearly massless particles that barely interact with matter. Trillions of neutrinos from the sun pass through your body every second, yet almost none interact with your atoms. These ghostly particles were once thought to be massless, but experiments in the late 1990s and early 2000s revealed that neutrinos do have tiny masses, less than 1/millionth the mass of an electron, but not zero. This discovery earned the 2015 Nobel Prize in Physics and had profound implications. If neutrinos have mass, they must travel slightly slower than light speed. The Super Kamiokande detector in Japan and the Sudbury Neutrino Observatory in Canada detected neutrinos from the Sun and showed they oscillate between different types during their journey, a phenomenon that can only occur if neutrinos have mass. This confirmed that even these nearly massless particles obey the cosmic speed limit. In 2011, the Opera experiment in Italy announced a shocking result. Neutrinos appeared to arrive 60 nanoseconds earlier than light would have traveled the 730 kilometers from CERN. This would have been revolutionary, overturning a century of relativity. But science demands extraordinary evidence for extraordinary claims. Other experiments couldn't replicate the result. 6 months later, Opera discovered 2 technical errors: a miscalibrated oscillator and an improperly connected fiber optic cable. When corrected, the neutrinos traveled at exactly the speed they should, just below light speed. This episode beautifully demonstrates how science works. An unexpected result was announced, scrutinized, tested, and ultimately corrected. The researchers didn't hide their mistake, they acknowledged it and moved forward. The speed of light limit survived another test, and our understanding deepened. Every time we challenge this cosmic boundary, we confirm its reality and learn more about the universe's fundamental structure. The search for physics beyond the standard model continues at accelerators worldwide. The Large Hadron Collider is currently being upgraded to higher energies and collision rates. Future projects like the proposed Future Circular Collider or the International Linear Collider will push even further. These machines will accelerate particles to speeds even closer to light speed, testing relativity at unprecedented precision. But no physicist expects to break the speed limit. Instead, they're probing what happens at nature's most extreme energies while respecting that ultimate boundary. Dark matter presents another fascinating connection to the speed of light. This mysterious substance comprises about 27% of the universe's mass energy, but doesn't emit, absorb, or reflect light. We detect it only through gravitational effects on visible matter. Whatever dark matter is, and we still don't know, it must be made of particles that obey relativity. Even exotic, unknown particles can't exceed light speed. The Bullet Cluster, 2 colliding galaxy clusters observed by the Chandra X-ray Observatory and other telescopes, provides dramatic evidence for dark matter. When the clusters collided, the hot gas in each cluster interacted and slowed down, while the dark matter passed through relatively unaffected. Gravitational lensing maps show the dark matter separated from the visible gas, demonstrating that dark matter exists as actual particles rather than being a modification of gravity. These dark matter particles, whatever they are, must have traveled at speeds below light speed during the collision. If they were massless and traveled at light speed like photons, they couldn't cluster gravitationally as observed. The fact that dark matter forms halos around galaxies and structures throughout the universe tells us these particles have mass and therefore can't reach light speed. Even mysterious, invisible matter respects the cosmic speed limit. Now let's explore what the speed of light means for the structure of atoms themselves. The fine structure constant, which I mentioned earlier, is approximately 1/137. This dimensionless number emerges from the speed of light, the electron charge, and Planck's constant. It determines how strongly electrons bind to atomic nuclei, how atoms emit and absorb light, and essentially all of chemistry and biology. If the speed of light were different, this constant would change. Even a small variation would have dramatic consequences. If the fine structure constant were slightly larger, electrons would orbit closer to nuclei, chemical bonds would be stronger, and stars might burn differently. If it were slightly smaller, atoms might be too loosely bound to form complex molecules. The speed of light isn't just a speed. It's woven into the fundamental constants that make our universe capable of supporting structure and complexity. Astronomers have tested whether the fine structure constant changes over cosmic time by studying the spectra of distant quasars. These extremely bright galactic nuclei are so distant that their light has traveled for billions of years to reach us. By examining the absorption lines created when this light passes through gas clouds, Astronomers can measure the fine structure constant billions of years ago and compare it to today's value. The Very Large Telescope in Chile and the Keck telescopes in Hawaii have conducted these measurements with extraordinary precision. The results show that if the fine structure constant has changed at all over the past 12 billion years, the change is less than a few parts per million. The speed of light, and the physical constants depending on it, appear to be truly constant across cosmic time and space. Black holes provide another profound connection to the speed of light limit. At the event horizon of a black hole, escape velocity equals light speed. Inside the event horizon, not even light can escape. This creates an absolute boundary in spacetime. Once something crosses the event horizon, it cannot send signals or information back out. The region inside becomes causally disconnected from the rest of the universe. The Event Horizon Telescope, a global network of radio telescopes working together, captured the first image of a black hole's shadow in 2019. This black hole, in galaxy M87, has a mass 6.5 billion times that of our Sun. The image shows a dark region, the shadow cast by the event horizon, surrounded by a glowing ring of hot gas orbiting at speeds approaching light speed. The gas in that accretion disk experiences extreme relativistic effects. Material on the side moving toward us appears brighter due to relativistic beaming. Its radiation is concentrated in the direction of motion. Material on the receding side appears dimmer. Time dilation is so severe that gas near the event horizon experiences time passing much slower than in the outer regions. The black hole's environment is a natural laboratory for extreme relativity. Near a black hole's event horizon, space is so warped that you'd need to travel faster than light to hover in place, to not fall in. This seems paradoxical since nothing can exceed light speed. The resolution is that you simply can't hover at the event horizon. You must either stay outside, where escape is possible, or cross the horizon and fall inexorably toward the singularity. The speed of light limit and the structure of spacetime around black holes are intimately connected. Hawking radiation, theoretically emitted by black holes, also connects to the speed of light. Stephen Hawking showed in 1974 that quantum effects near the event horizon should cause black holes to radiate particles and slowly evaporate. This radiation travels at light speed or slower, carrying energy away from the black hole over enormous timescales. A solar mass black hole would take 10 to the 67 years to evaporate, far longer than the current age of the universe. While Hawking radiation hasn't been directly observed from astrophysical black holes, it's far too faint. Researchers have created analog systems in laboratories. These use sound waves in flowing fluids or light in nonlinear media to create acoustic or optical event horizons. The analog Hawking radiation from these systems has been detected, confirming the theoretical predictions. Even in these analogs, information propagates at the speed of sound, or the effective light speed in the medium, never faster. Let's talk about wormholes, hypothetical tunnels through space-time that could connect distant regions of the universe. These emerge as solutions to Einstein's equations, suggesting they might be possible in principle. If wormholes exist, you could potentially enter one location and emerge at another far away, seemingly traveling faster than light. But there's a catch. Actually, several catches. First, traversable wormholes require exotic matter with negative energy density to keep them open. Ordinary matter has positive energy density and would cause wormholes to collapse. While quantum effects can create small amounts of negative energy through phenomena like the Casimir effect, scaling this up to macroscopic wormholes faces severe limitations. The quantum inequalities, developed by physicists in the 1990s, show that negative energy is severely constrained in magnitude and duration. Second, even if you could create a stable wormhole, using it for faster-than-light travel runs into causality problems. Kip Thorne and his colleagues showed that you could potentially use wormholes to create closed time-like curves, paths through space-time that loop back to your own past. This would allow time travel with all its associated paradoxes. The universe seems determined to prevent this, possibly through quantum effects that destroy wormholes before they can violate causality. Third, traversing a wormhole might not actually allow faster-than-light travel in the way you'd expect. While you might arrive at a distant location quickly, The light that traveled through normal space might still arrive first from some reference frames. The geometry of spacetime with wormholes is subtle, and what counts as faster than light depends on how you measure distance and time. The cosmic speed limit appears to survive even in these exotic scenarios. The mathematics of general relativity allows for many exotic solutions: wormholes, time machines, warp drives. But just because the equations permit something doesn't mean it's physically realizable. Many of these solutions require conditions that may be impossible to achieve, like negative energy densities exceeding quantum limits or singularities in spacetime that might be forbidden by quantum gravity. Nature may allow these solutions mathematically while making them practically impossible. String theory, one of the leading candidates for a theory of quantum gravity, suggests that spacetime might emerge from more fundamental structures. In this view, the speed of light limit might not be a fundamental law, but rather an emergent property of how spacetime arises from underlying quantum mechanics. Some string theorists propose that space and time themselves might be woven from quantum entanglement, with the speed of light representing the maximum rate at which quantum information can propagate through this entangled network. Loop quantum gravity, another approach to quantum gravity, suggests that space itself is quantized at the Planck scale, about 10 to the negative 35 meters. At this unimaginably tiny scale, space would be discrete rather than continuous, composed of fundamental units like atoms of space. If this is true, the speed of light might represent the maximum rate at which information can hop from one quantum of space to an adjacent one, like a speed limit imposed by space's fundamental granularity. The Planck scale connects multiple fundamental constants: the speed of light, the gravitational constant, and Planck's constant from quantum mechanics. At this scale, quantum gravitational effects become important. The Planck length defines the smallest meaningful distance, the Planck time the shortest meaningful duration, and the Planck energy the scale where quantum effects and gravity become equally important. All these quantities depend on the speed of light, showing how deeply it's embedded in physics. Experiments are trying to detect quantum gravitational effects by looking for tiny deviations in how light propagates over cosmic distances. If spacetime is quantized, high-energy photons might travel slightly slower than low-energy photons due to interactions with spacetime's quantum structure. The Fermi Gamma-ray Space Telescope has looked for such effects by timing photons from distant gamma-ray bursts, finding no evidence of energy-dependent speed variations to incredible precision. These null results tell us that if spacetime is quantized, the effects are even subtler than many theories predicted. The speed of light appears constant across all energies and distances we can measure, suggesting it's truly fundamental. Every test strengthens our confidence that this cosmic speed limit isn't just an approximation, but an exact feature of nature. Now let's consider the implications for alien civilizations and interstellar communication. If intelligent life exists elsewhere in our galaxy, they face the same speed of light constraint we do. A message sent to a civilization 1,000 light-years away would take 1,000 years to arrive. Any reply would take another 1,000 years to return. A single exchange of messages spans 2,000 years, longer than recorded human history. This means that interstellar communication, if it happens, must be patient. We can't have conversations across light-years. We can only send messages knowing that responses will come to our distant descendants. The SETI project, Search for Extraterrestrial Intelligence, listens for radio signals from space, knowing that any signal detected would be ancient by the time it reaches us. We might be hearing the voice of a civilization that has already fallen silent. The Arecibo message, sent toward the globular cluster M13 in 1974, will take about 25,000 years to reach its destination. Any reply, if one comes, won't arrive for 50,000 years. This isn't a limitation of our technology, it's a fundamental constraint imposed by the speed of light. Even civilizations millions of years more advanced than us cannot send information faster than this cosmic speed limit. Some scientists have proposed that advanced civilizations might use entangled particles for instantaneous communication. But as we discussed, quantum entanglement can't transmit usable information faster than light. The correlations are instantaneous, but extracting meaningful information requires classical communication channels limited to light speed. The universe maintains its prohibition on faster-than-light messaging even at the quantum level. The Fermi paradox asks, if the galaxy is billions of years old and should have had time for civilizations to spread across it, where is everybody? One answer might be that the speed of light limit makes interstellar travel and colonization so difficult that even advanced civilizations rarely attempt it. The distances are so vast, the travel times so long, that civilizations might remain confined to their home systems, making the galaxy a collection of isolated islands of intelligence. But perhaps the speed of light limit is a gift rather than a curse. It gives each civilization time to develop independently, to create unique cultures and perspectives. It prevents rapid homogenization across the galaxy. It ensures that when we finally do encounter others, they'll have something genuinely new to teach us, perspectives shaped by billions of years of separate evolution. The cosmic speed limit creates diversity in the universe. For our own future, the speed of light shapes what's possible. With current technology, reaching even the nearest stars would take tens of thousands of years. The Voyager spacecraft, traveling at about 17 kilometers per second, would take 70,000 years to reach Proxima Centauri if it were headed that direction. Even at 10% light speed, a velocity far beyond our current capabilities, the journey would take 42 years. The Breakthrough Starshot initiative proposes using powerful lasers to push tiny spacecraft equipped with light sails to 20% light speed. At this velocity, these miniature probes could reach Proxima Centauri in about 20 years, sending back data about potentially habitable planets. This ambitious project pushes the boundaries of current technology while respecting the cosmic speed limit. We're learning to work within nature's constraints rather than fighting against them. Time dilation offers one slim advantage for interstellar travelers. A spacecraft accelerating continuously at one Earth gravity, providing comfortable artificial gravity for the crew, could theoretically reach the galactic center in about 20 years of ship time, though hundreds of thousands of years would pass on Earth. The travelers would be exiles from their own time, arriving in a future they can barely imagine. The speed of light limit makes every interstellar journey a one-way trip, not just in space, but in time. If you are still watching, please subscribe to the channel and give a thumbs up. And if you enjoyed this video, I am sure you will love this other one. The rarest object in the universe. In this video we explore the most extraordinary and elusive cosmic phenomena ever found by astronomers. See you there.